Hello, welcome. In this lecture, we will emphasize some of the important properties of sequences of real numbers and investigate the limits of several basic sequences that are frequently encountered in the study of analysis. Our first result involves algebraic operations on convergent sequences. Theorem. If a sub n and b sub n are convergent sequences of real numbers with the limit of a sub n as n approaches infinity equals to a, and the limit of b sub n as n approaches infinity equals to b, then the limit of a sub n plus b sub n as n approaches infinity equals to a plus b. In other words, the limit of the sum of the sequences equals to the sum of their limits. The limit of a sub n times b sub n as n approaches infinity equals to a times b. In other words, the limit of the product of sequences equals to the product of their limits. Furthermore, if b is not equal to 0 and b sub n is not equal to 0 for any n, then the limit of the quotient a sub n over b sub n is equal to a over b. In other words, the limit of the quotient of sequences equal to the quotient of their limits. Let's have a look at the proofs of the statements A and B. Let epsilon be given. Since the sequences a sub n and b sub n are convergent, there exist positive integers n sub 1 and n sub 2 such that the absolute value of a sub n minus a is smaller than epsilon over 2 for all indices n greater than or equal to n sub 1. And the absolute value of b sub n minus b is smaller than epsilon over 2 for all indices greater than or equal to n sub 2. Now we define capital N equals to the maximum of n sub 1 and n sub 2. Therefore, for all indices n greater than or equal to the capital N, the absolute value of the quantity a sub n plus b sub n minus a plus b can be rewritten as the absolute value of a sub n minus a plus b sub n minus b. Now, in the right-hand side, we apply the triangle inequality to obtain this inequality. Now, the absolute value of a sub n minus a is smaller than epsilon over 2 from here, and the absolute value of b sub n minus b is smaller than epsilon over 2 from here. So the quantity in the left-hand side is strictly smaller than the quantity in the right-hand side. Therefore, by definition, the limit of a sub n plus b sub n as n approaches infinity equals to the quantity a plus b. In other words, the limit of a sub n plus b sub n as n approaches infinity equals to the sum of the limit of a sub n and the limit of b sub n as n approaches infinity. Whenever the limit of a sub n and the limit of b sub n as n approaches infinity exist. Now, to prove the statement B, let epsilon be given. There exist positive integers n sub 1 and n sub 2 such that for all indices greater than or equal to n sub 1 and for all indices n greater than or equal to n sub 2, we have the absolute value of a sub n minus a is smaller than square root of epsilon over 3, and the absolute value of b sub n minus b is also smaller than the square root of epsilon over 3, respectively. The choice of such complicated quantities here, the square root of epsilon over 3, will be made clear later in the proof. Also, there exist positive integers n sub 3 and n sub 4 such that the absolute value of a sub n minus a is smaller than this quantity, and the absolute value of b sub n minus b is smaller than this quantity. Notice these two quantities are positive. For all indices greater than or equal to n sub 3 and for all indices greater than or equal to n sub 4, respectively. Now we define a positive integer n such that it is the maximum of all those four positive integers n sub 1, n sub 2, n sub 3, and n sub 4. Therefore, for all indices n greater than or equal to n, we can write the absolute value of the quantity a sub n, b sub n minus ab as the absolute value of a sub n times b sub n minus b plus b times a sub n minus a. Here we have introduced an extra term a sub n minus b, and we balanced that with this term b times a sub n. In the next step, we also introduced some extra terms. For example, we write a sub n as a sub n minus a times b sub n minus b. So we introduced negative a times b sub n minus b as an extra term. So we balanced that with the help of this term, a times b sub n minus b. And now we apply the triangle inequality to get this step. Recall that the triangle inequality for three quantities can be written as this is the extended version of the triangle inequality for three quantities. Now we see that the term here, the absolute value of a sub n minus a, was assumed to be smaller than the square root of epsilon over 3. And the term here, the absolute value of b sub n minus b, was assumed to be smaller than positive square root of epsilon over 3. And the quantity b sub n minus b, its absolute value, was also assumed to be smaller than epsilon over 3 times 1 plus absolute value of a. So we have the product. Similarly, the quantity, the absolute value of a sub n minus a, was assumed to be smaller than epsilon over 3 times the quantity 1 plus absolute value of b. So we have the product. Now if we simplify the first term here, it becomes epsilon over 3. And since the quantity absolute value of a over 1 plus absolute value of a always smaller than 1, so we can multiply both sides by a positive quantity epsilon. So we get this inequality here. Similarly, for the third term, we would have this inequality. Therefore, we prove that the left-hand side is smaller than this sum, which is simply the epsilon. In other words, the limit of the product a sub n b sub n as n approaches infinity equals to the limit of a sub n and the limit of b sub n as n approaches infinity. Whenever the limit of a sub n and the limit of b sub n exist. So we have proved the limit of product of n terms of two sequences equals to the product of their limits. Theorem. Let a sub n and b sub n be sequences of real numbers. If b sub n is a bounded sequence and the limit of a sub n as n approaches infinity equals to 0, then the limit of the product a sub n b sub n as n approaches infinity is equal to 0. So this theorem says that if one of the sequences is bounded and the other sequence has limit 0, so the product of these two sequences has limit 0. Let's have a look at the proof of this theorem. Since the sequence b sub n is bounded, there exists a positive real number m such that the absolute value of b sub n is smaller or up to equal to m for all indices n. Now let epsilon be given. Since the sequence a sub n is convergent, there exists an index n in the set of natural numbers such that the absolute value of a sub n is smaller than epsilon over m for all indices n greater than or equal to n. Therefore, the absolute value of the product a sub n and b sub n can be written as the product of the absolute values of a sub n and b sub n, which is smaller or equal to the absolute value of a sub n times m. This is smaller than or equal to m. And again, the absolute value of a sub n is smaller than epsilon over m. So we have the absolute value of a sub n, b sub n is smaller than the quantity epsilon for all indices n greater than or equal to n. And this proves that the limit of the product a sub n, b sub n as n approaches infinity equals to 0. Let's have a look at an example of the previous theorem. Consider the sequences 1 over n and sine of n. Since the limit of 1 over n as n approaches infinity is 0, and the sequence sine of n is bounded because the absolute value of sine of n is smaller or equal to 1 for all indices n, then by the theorem 7.1.2, we have the product a sub n, b sub n, which is sine of n over n. The limit of it equals to 0. So we considered a sub n equals 1 over n and b sub n equals sine of n. So the product is sine of n over n. Since this has limit 0 and this is bounded, so by the previous theorem, the product sequence has limit 0. In the following figure, we plot first few terms of the sequence sine of n over n. In this figure, we see that the terms of the sequence n sub n over n are getting closer and closer to the point 0. Note that if the sequence b sub n is not bounded, then we may have the limit of the product a sub n, b sub n as n approaches infinity not equals to 0. For example, consider the sequences a sub n and n. Here we have the limit of a sub n, meaning 1 over n, equals to 0, but the sequence of n's is unbounded. But the product sequence has limit 1. Proposition: if a sub n be a sequence in real numbers, then the limit of a sub n equals a if and only if the limit of a sub n minus a as n approaches infinity equals to 0. So this proposition simply allows us to move the limit a to the left-hand side under the limit expression. Let's have a look at the proof of this proposition. Please pause the video and try to read the proof, or please consult the notes for the details.